So before we move on to the fifth problem, there's something in theories we'll just revise very quickly. Stochastic and independent exogenous variable. If x is stochastic, then the covariance of x and ut is 0. Indeed, because x is exogenous and stochastic is changing, and with AR1 structure given in stationary AR1 process, x is equal to phi xt minus 1 ut, where ut is IID with 0 mean and eta square variance. It's similar to ut being stationary. Ut is stationary here and mixing, and satisfies the weak law of large number, which is the mean of summation of the x square, exogenous variable square. Asymptotically, the expected value of x square becomes the variance eta square divided by 1 minus the autoregressive coefficient or autoregressive parameter phi, 1 minus phi naught square. So eta square divided by is the variance and autoregressive parameter. The product process of xtut is therefore also stationary, obviously, because ut is stationary. So xtut asymptotically we converge to the regressive parameter, so it is also stationary. Mixing and satisfy mixing central limit theorem, which was, well, we are taking yt whose distribution depends on 0 mean, and the standard deviation is j OPD, which is OP's outer product gradient. J is first is the limiting property y square by t just like x square, or expected value of y square plus 2 into j equals 1 to infinity yt minus expected value of yt depending on its lag yt minus 1. So this is the variance of y and basically covariance of y and its own lag, 2 into j equals 1 to infinity. So this is what asymptotically we want to measure the asymptotic yt. This is how we measure the asymptotic yt. This is how we measure the asymptotic xt. Yt is weakly stationary. J shows weakly stationary means, well, some of its moments are stationary. J shows asymptotic variance of sample mean depends on variance and all the autocovariance, which is the theory of mixing conditional log likelihood function. So to look further into this, we look into the product of xtut, variance, then covariance. Obviously the variance of the mixing CLT suggests variance and all autocovariances. What is the mixing CLT just suggested? It suggests that J shows asymptotic variance of sample mean depends on variance and all autocovariances. Xt minus j, ut minus j, fine. Variances and all autocovariances, we break it further. For covariance of xt with its lag and ut with its lag, and we know variance of xt is eta square 1 minus phi square, and we know variance of ut is the all that we have been dealing with up till now, the asymptotic variance sigma square 1 minus rho square. This is also the same, except for xt minus j. For the lag, we bring in the autocorrelation, autoregressive parameter phi naught j, and rho naught j is the autocorrelation parameter with sigma square. That's all, nothing else. So we take common, and we are left with 1 plus phi naught rho naught, 1 minus phi naught rho naught, eta square 1 minus rho square, well, sigma square 1 minus phi square. So asymptotically the variance becomes, with relative asymptotic efficiency, when we are doing this is the asymptotic variance, which is beta hat least square. When we do we just did this, you see, this is coming from the Harvey study, the Harvey estimation that we compared with maximum likelihood estimation of beta hat. So this is it, and maximum likelihood estimation of beta hat. So when we compare them, all this crosses out and we are left with only 1 plus rho square divided by 1 minus rho square. This is what we need to do now. Okay, and we need to see if how more is the asymptotic variance of OLS compared to asymptotic variance of MLE. So this is the asymptotic variance of OLS and this is the asymptotic variance of maximum likelihood estimation. We just need to yeah, this is the asymptotic variance of OLS and this is the asymptotic variance of maximum likelihood estimation. We just need to compare them, that's all. Sigma square by eta square. Asymptotic variance of maximum likelihood estimation is sigma square by eta square divided by t minus 1 or 1 by t minus 1 inverse of information matrix, that's all. So this is the background of this problem, and now we're gonna look into the problem itself, and the problem is titled auto efficiency. So let's look into auto efficiency. The problem is this is the equation beta naught beta 1 xt ut rho ut vt. The following Monte Carlo experiments are based on the population parameter values which are given to us: beta naught beta 1 rho sigma square. Simulate the model for 5000 replications and sample sizes of these, where the exogenous variable is a deterministic time trend. Compute mean squared error with beta beta hat estimated minus 1 beta 1, just like before actually. Beta 1 beta hat minus beta naught squared divided by the replications of the maximum likelihood and least square estimators of beta naught and beta 1, and discuss the relative efficiency of the two estimators. Well, this many 1 2 3 4 5 6 6 columns will be replicated. Now we want to do it with x being sine twice pi t divided by t, a deterministic sinusoidal trend. Repeat part A, where the exogenous variable is a stochastic time series. Now exogenous is a deterministic trend. Now if exogenous is a stochastic trend with having with is residual being 0 mean and 0.0036 variance, in the simulation treat xt as stochastic by redrawing wt in each replication. Show that as the sample size increases, the ratio of maximum likely mean squared error of the least square and the maximum likelihood estimator for the slope parameter beta 1 converges to asymptotic efficiency ratio. Obviously that means the ratio efficiency, they're converging, which I'm trying to show that as replications increase, they are converging. Repeat exercise for different values of rho and phi. Demonstrated the asymptotic efficiency ratio is independent of the parameter beta naught and beta 1 by choosing different values. Quite a lot of things to do, but I don't think a lot of things will be done in the codes. First we see if we are needed to create any we need a local function. So we have beta y x and a flag. Okay, flag, either we raise the flag or we don't raise the flag. So and beta naught is b1, beta 1 is b2. Obviously we need to set this inverse Rexer trimmer, this package 0 1 repeat matrix. We need to load the package of MATLAB, byx and then flag beta naught b1, beta 1 beta 2, rho 1 is 10h, b3 we have explained this before. Y beta naught beta 1x, fine. V is u2 to the n rho 1 to the n minus 1, beautiful. We didn't do trim this time. We can also do this, which actually is the same thing. We did trimmer in R. Now we could have done u minus 1, then length of minus length of u. That could have been given you the same thing. We instead of like the trimmer function, we have seen that. Then the exact maximum likelihood estimation, full maximum likelihood estimation, exact one is computed with t equals 1 and t is greater than 1 for maximum likelihood estimation, just like before. No tweaks here. Then if flag is generated, then we will do so flag is saying either in one function we are saying either do conditional maximum likelihood or do a full maximum exact maximum likelihood or a full maximum likelihood. So full will consider both conditional and unconditional, while as a conditional will only consider the conditional portion. So previously we did this in two functions, now we are bringing them in one, which is a much better thing. If flag, in third bracket, in first bracket, which is really good. Else log L, return log L. Good job. So this is a beautiful program. So let's see how we proceed. First we name this as a function and we start generating. We're saying t is equal to 200, beta naught, beta 1, rho 1, sigma square is given to us, theta naught is all the parameters in column combined, so we simply combine all these parameters, just combining in columns, that's all. Phi 1 is 0.6, this is also given. Sigma square is 0.0036, fine. Number of draws. So there are two we are just gonna see one example. There are two instances where one x is treated as a fixed or x is treated as a sinusoidal. So when it's treated as fixed, simply 1 to t multiplied to random number of t minus 1. So that's all. And when it is sinusoidal, this is the code, that's all. So just multiply. When it's fixed, then we just, with the fixed number, we just create a random number. So we have number of draws 500 times, isn't it? We have 5000 replications. I think it is 5000. This is a mistake, or yeah, it should be 5000. Theta exact so is zeros n draws and 4 columns, because all the thetas are here. N draws 4 columns. Beautiful. We are using zeros from MATLAB instead of just replicating, so we can use this function as well. Theta conditional zeros, n draws 4, theta OLS zeros, n draws 4, fine. PB text progress bar, minimum 0, maximum n draws style 3. For k is equal to 1 to n draws, or for k in sequence of n draws, zeros, ones and repeat matrix, good. K in sequence, k in sequence and n draws, fine. 1 to n draws. Generate, first we generate data v, random number square root of sigma square into random number t minus t rows 1 column. So square root of sigma square r norm t, because this is not uniform distribution. Then the rexrr, just like before, rexrr c bind, column bind v, column bind x y naught and row. Then w square root of sigma square into random number of t, square w. So beautiful, we are generating this data with for the case when x is not fixed, rexrr w instead of v now. W square root of 1 by 1 minus phi square w, and phi 1, y is equal to beta naught plus beta 1 x plus u. Xt if not fixed. When x is fixed and when x is not fixed, then we generate x, which is also a recursive series. Okay, now data has been generated, w, x and y. This is the new thing here. If x is not fixed, then we run a recursive series on x with the residual of x coming up here in w, right? So 1 minus phi w1 phi. This is something we have also shown. We have also seen. How? Let me show you. Amazing. See, this is for u, this is for x, this is so sigma square rho when x is not fixed, v and rho, w and phi. So phi, w and phi when x is not fixed, then we have w and phi here instead of w, eta square. So otherwise w and phi, otherwise we use sigma and rho, v and rho. Okay, when x is fixed, we estimate u, residual u when x is fixed with rho. When x is not fixed, when we are generating x also, v square and phi square, same thing, you see. Okay, y is equal to beta naught beta 1x plus u. X and u both has been generated beautifully. Then exact maximum likelihood estimation. So for exact, we don't want to raise the flag is 0, so the whole thing will run. Fn in search, whenever, remember, when do we use fn in search for maximization? When we have flag. You see, this option flag is included in the function of fn in search. That's why fn in unc and fn in search gives you the same maximization optimization function. Neglog byx flag theta, so flag false. Instead of 0 we say flag is false. Optimization theta naught is the part. Neglog yyxs flag method bfgs part. Theta exact k rows for all the columns, which is all the columns, meaning well, k rows for all the columns. Storing the theta here in theta exact for up to k rows for all the columns, we are storing, you know. Oh, this thing is under for loop as well. The whole thing, k rows for all the columns. That's why we're giving it a structure, because k is number of rows. We're storing beta naught beta 1, under which coming a row which has a tangent function with it, so that it is fixed. We are doing it in a shortcut manner. Absolute value of theta 4 is last one, which is the last parameter sigma square variance. Beautiful. Absolute value of theta 4. See, so theta exact k, we don't need to put all the columns here in R, just the third brackets created. So combine theta 1 to 10h theta 3, absolute value of theta 4. OLS, this is conditional. Maximum likelihood is we raise the flag now. That's all. Everything else remains same. Nothing else changes. We just raise the flag. In both cases, we are still estimating variance. And then OLS. OLS is once T1 column bind x, column bind x, beta hat OLS is linear model of y x minus 1 coefficient. So column bind once and x. First we are doing a column bind on this, not combining, column binding, and then So we don't want a one vector, we need two, or a matrix. We're creating a matrix with x, right? So E is equal to y minus t1x multiplied to beta hat olx y minus xs. Okay, this has many usage. We could have done that in MATLAB too, into beta hat ls, and mean E square is sigma square ls, rho ls is u1 n minus 1 regressed upon 2 end. Great. So this trimmer E10 regressed on trimmer E01. So the denominator will go up. E10 trimmer E0. In last we are first we are trimming the first row, here we are trimming the last row. Again we'll store beta hat ls, sigma square ls, rho ls, everything. Close to be great. So we have MSc exact, compute statistics mean, theta exact minus repeat matrix, theta naught, n draws 1 square. Okay, so theta naught transpose theta naught, which was theta 1 exact, theta naught is fixed, the theta parameters is fixed. So we are creating a repeat matrix so that this thing comes again and again and again. Very simple. Squared. That's all. So column means column means is the function against mean. And then there is quite a lot of stuff here. Mean, bias, mean square error. Root mean square error is simply square root of mean square error. Bias is 100, mean theta exact means theta naught. We already done that. Okay, they want us to do it again. Fine. So we just copy and paste. Efficiency. We do efficiency test and we see as number of samples increase, efficiency increases. So that was number 5. Then comes the next problem, which is auto Hatanaka. Is an Hatanaka estimator we are gonna talk about. Okay, I think I'll grab a cup of coffee for a break. So why Hatanaka estimator is another important estimator similar to Harvey's estimator? When we are optimizing log likelihood, the optimization things we have just seen, optimization problems, maximum likelihood estimator is consistent even including lag dependent variable, whereas becomes inconsistent, you see, because when you include the lags, it is not it becomes autocorrelated with the residual. And in maximum likelihood we can invoke Martingale central limit theorem as gradient vector, where none of the variables are associated with their lags. Asymptotic normality is obtained, and still we represent Martingale difference square. Inclusion of yt minus 1 is part of conditioning set of information. To get the efficiency for OLS, Hatanaka is an alternative estimator. Hatanaka is based on OLS but is an alternative estimator. And there is Hatanaka estimator. Consider a model where beta naught, beta 1, xt plus alpha 1, yt minus 1. You see the lag is here. When you have lag, OLS becomes inconsistent. Now with Hatanaka, it might remain consistent. That's all. or Anika is an efficient estimator when similar is the case. Rho ut minus 1, assuming ST is deterministic, prove that covariance of ut yt minus 1 is rho naught sigma square. Basically in these cases 1 by 1 minus alpha naught rho naught 1 minus rho 1 square, rho naught square. So this is the Anika estimator where rho naught sigma naught square and alpha naught represent the population equivalents of p rho alpha and sigma square, letting the exogenous variable be well deterministic with mean minus 0.5. it will change by the means. We did this thing before, and 0.5 variance. Population parameter values of theta naught are beta naught, beta 1, alpha naught. Verify the results by simulating the model for 1 million times and compute sample covariance of yt minus 1 and ut. Show how this model can be estimated using Gauss-Newton. Compare the sampling properties of Anika estimator for various sample sizes. So various sample sizes with the maximum likelihood estimator as well as with the OLS estimator. Treat xt as fixed. Basically here we are gonna check efficiency with Anika estimator. That's all. Nothing else. So let's see. Let's start with looking if there is any local function. Obviously streaming will be there. So quite a few local functions. First we are to simulate the data. Yx simulate data t. A function is created named simulate data. Yeah, sure. Y where okay, they're not gonna, R has not used the simulate data function. Given 0.6, 0.4, beta 2, 0.2, alpha minus 0.5, these are given. Rows are also given. So with these our omega is also given to us. Omega is also given to us. Which is 1.5.51. Because alpha is 0.5, variance 0.5. So omega is 1.5.51. 1 minus beta 2 minus beta 1 1 minus alpha 0 1 0 minus alpha 2, non-diagonal and diagonal. Exogenous is because 10 into random t1, 3 into random number t1. Two exogenous variables are being created. Okay, 10 into random t1, 3 into random number of t1 because yeah, given in the question. 10 is random t1, t is random number of t1, fine. Disturbance is v. T2 Koleski of omega. Disturbance is v is random number t, rows 2 columns. Koleski and u zeros. T2 for I is equal to 2 to t. ui ut minus 1 plus rho 1 1 rho 1 1 ut minus 1 plus rho 2 2 ut minus 1 for the first column, and for in the second column vi1, then I choose rho 2 1 ut minus 1 first column, rho 2 2 ut minus 1. Obviously there will be two, it's a AR2 model, so there will be 2 rows plus vi2 rows, 2 columns. For I is equal to 2 to t, and so disturbances are created randomly. Exogenous variable. Simulate the model by simulating the reduced form. yi minus xi in inverse. Okay, minus a by b, if you can remember, minus x plus u by b. The model is being simulated by simulating the reduced form. What are you doing? We're supposed to look into Hatanaka. I'm really sorry. So that's fine. Log likelihood function at each observation. First, neg log byx, beta naught, beta 1, alpha 10h, beta 3, rho 1, 10h, beta 4, sigma square. Well, rho 1 and rho 2, you have two correlation coefficients in this problem. Yeah, we're supposed to have rho naught and rho 1, I guess, right? 1 alpha, beta 1 is there, alpha is also there. So rho 2 is absolute value, so full and conditional, t equals 1, t is greater than 1. Oh no, this is the equation. So not beta 1 minus alpha 1, trimmer y01, x10. So trimmer y10 and minus alpha 1 trimmer y01. See, this is the progression in steps. Beta naught, beta 1 trimmer x10. Generally, when we are doing OLS, then we also do trimmer x01, but we are not doing OLS here. V is trimmer u10, trimmer u01, fine. Then this is the conditional log likelihood function. Trimmer y10, trimmer y01, minus beta naught, minus beta 1, trimmer x10. Log likelihood function, then two-step Hatanaka two-step efficient estimation estimator. Hatanaka y, x and t. Y bar trimmer y10. Okay, y variable is trimmer yt minus 1, y10. Then x var is ones t minus 1 rows, 1 column, ones t minus 1 1. So we're doing column bind. Second column, column bind, 1 t minus 1 1, trimmer x10, trimmer y01. So y10, y01. Okay, trimmer y10, trimmer y01, they give you the same dimension. Trimmer x10, 1 t minus 1 1, so that all these remain same. Z bar, same thing. So instrumental variable initial estimates of mean parameter. Beta instrumental variable is inverse of z bar transpose x bar multiplied to z bar transpose x bar. So this one divided by, so zy divided by zty divided by zt transpose x. All right. Okay, so z transpose y divided by z transpose x, very simple. Okay, and u is y minus beta ix, y minus beta instrumental variable x. So you have you estimated residual. Now you estimate rho. Rho is trimmer u01. This is regressing ut on ut minus 1. So trimmer u10 is regressed on trimmer u01. Y bar is y20 minus rho trimmer y11. See, steps remain, the size of the steps remain same because you remove 2. Here you remove 1 in the beginning, 1 in the end. Rho trimmer y11. X bar column bind 1 t minus 2 1. 1 t minus 2 1. Trimmer x20 minus rho trimmer x11, just like before. Trimmer, now we have already done this, trimmer y20. Now we do trimmer y11. We'll start from trimmer y11, we'll end it in trimmer y02. Okay, we did 20 before. Trimmer y02. So ones in x we have ones. Then we have similar to this y bar, we have x fixed, x estimated. Then we have trimmer y11 because we already did yt minus 2 minus yt minus 1. Here yt minus 1 minus yt, trimmer y02, and then finally trimmer residual u01. This is exactly the same thing, no change at all. So regression on transform variable and updating of row. So you have x bar and y bar, so you regress them to get b, and then row gets updated. Row is row plus b4, which is b4 is row itself. Then we do compute the residual variance after updating row. We have compute the residual variance. V is trimmer y20, this equation, once t minus 2 y20 minus once t minus 2. So basically v, here we had v, right? We are taking everything on the left hand side. So y, then this is the x portion, y1 b113, right, into b13, which is row, trimmer y11 into b13, trimmer y11 into b13 minus row, trimmer x20, once t minus 2, trimmer x20, okay, trimmer y11 b13 into minus row into trimmer y11 minus a lot of things. Residual variance, my god, this is quite big. Compute residual variance. Okay, this is the x portion, that is all multiplied with the residual. What did I do? Variance, compute the residual variance. Okay, okay, I have removed the whole thing downstairs. Okay, let's fix it. Yeah, so you have y2 minus the x portion, x20, y1 beta 13, and row trimmer y11. x20, I'm not sure how this has been fixed. I need to look into. Okay, I think I know. My god, found it. Let me show you. This is v, ut minus row ut minus 1, yt minus bit xt, alpha yt minus 1. Now let's see yt minus bit xt. So this is the yt part, trimmer yt0 minus beta xt. This is the xt part, beta multiplied to the xt part, which is trimmer x20, trimmer y11, once t1. So this is the xt part, right? Yeah, once, then trimmer x20 minus row trimmer x11. Fine. So this is the xt part, and alpha yt minus 1. Alpha yt minus 1, this is beta xt 1 to 3 into 1 to 3, then alpha is rho yt minus 1, which is y11, then rho yt minus 1 beta xt minus 1 alpha yt minus 2, then the whole thing again. Yeah, this is something like that, then rho sigma square. So compute residual variance seems a bit difficult. We need further studying actually to do the residual. However, this is how it's look. Just remember, this is how the residual variance is being computed, and that's the equation. I think, yeah, rho trimmer y11 into 1 3. Yeah, this is the exact equation represented here. So how do we do Hatanaka then? So first we introduce the initial estimates, then we generate a random number minus 0.5 because u is minus 0.5 to 0.5, then v is square root of sigma square random number t1, our norm, then u with recursive estimation process, we recursively estimate u with y. This is the Beach-McKinnon method. Then beta naught etc beta naught beta 1 x plus u, which is in place of x we are putting it, then in place of y naught we are putting 0, and alpha is in place of coefficient alpha 1. That is how we put recursive estimation on y. So theoretical covariance is rho sigma square divided by 1 minus alpha 1 rho 1 into 1 minus rho square, and simulated is this theoretical and simulated 1 minus rho 1. So this is the theoretical, and simulated is simply covariance of trim y01 u10, that's all, yt minus ut. And Monte Carlo replication 100,000 times. X is again conditional. Hatanaka OLS we put in zeros, then 1 to n rows, generate data just like before, u and y, then maximum likelihood estimation estimates theta 1 to everything actually. Then Hatanaka estimation is, we just call it, that's all, we don't do anything here, we just call the Hatanaka estimator, that's all. And then OLS is how is done, rho general OLS, rho OLS, sigma square OLS, and then we compute the mean square errors and stuff. Hatanaka is quite big code, it might require to understand it more, especially it creates confusion in terms of lags, but I will just give a break here. Now the problem we'll deal with is gonna talk about systems with multiple models or multivariate models. So how does multivariate models work out? Basically starts from previous page. Yes, we have gone through this already. If you have multivariate models like y1t, y2t, you have multiple u's and v's, and your v is zero mean and sigma variance, and this is the reduced form if you can recall, where b was n by k, n by n, and a was n by k. Remember, rho is n by n, v is n by n. Need to remember the dimensions. And the multivariate model distribution is 1 by root over twice by, this is the probability distribution function of Vt, which is 1 by root over twice by n, absolute value of root over v, then exponential of the decomposition of v. And then with variable transformation technique we have shown you how we can transfer Vt to ut, which then becomes this equation. Instead of v we put ut minus rho ut minus 1 in all cases. Then we transform further ut to yt, and we have nothing but inside nothing changes except for the coefficient of y is multiplied with it, and y is simply dd of yt, where ut is this coefficient, or with reduced form equation we can estimate it. And this is the log likelihood function. The conditional log likelihood function is maximized with respect to BAPV. This is the usual way. So this should be an easy problem in autocorrelation system. Okay. So first, it's a lot of things we'll have to go through here. First, we need to simulate the bivariate model with these given data. The exogenous variable is uniform distribution in 0 mean and 10 standard deviation. x1t and x2t is 0 mean and 9 standard deviation. Standard variance is 10, variance is 9. So its normal distribution is uniform distribution. Estimate the model using conditional MLE. Perform an LR test, WALT test, and simulate the model with no autocorrelation, putting all the autocorrelations to 0. Very well, fine. So this we started discussing before. Obviously we're gonna do simulations, so we put the simulation. I will always encourage to include the library, MATLAB library. So first we simulate data. All these given to us, these are given to us, all these are given to us. Exogenous variable is very easy to calculate because you have two exogenous variable x1 and x2, because you have two y's. One is having a uniform distribution, so 10 random t1 are runif, and the other one is, well, where are the x's? Am I going too fast? I didn't do the simulation in R whatsoever. That might not be necessary. Okay, we'll come back to it later. So T1 disturbances is simply a random number, T rows 2 columns, because we will have 2 V's multiplied to omega, and we have 2 residuals. We'll always calculate residual with loop 2 to t, obviously 2 to t, because, well, starting from 2 we have 2 variables. I1 is row 11 u t minus 1, row 12, so row 1 1 ut minus 1 plus row 2 2 ut minus 1, because the equation suggested that, right? Because row 1 1 ut minus 1, row 2 2 ut minus 1, row ut minus 1, that's all. And we have row 1 1 ut minus 1, row 2 2, row 1 2 ut minus 1, u1 u2 u1 u2. So I minus 1 1, the first element, then the second element 2, row 1 2, row 2 1, first element, second element. Okay, row 2 1, row 2 2, all these are given to us, vi1 and vi2. See, exactly the same disturbance vector, very easy. Then simulate the model using the reduced form. So we just use the reduced form for if I equals 1 equals 1 to t. So we have the reduced form. Now we do the log likelihood function, theta yx. First tn size of y, t n row y, n column y. It's not easy in R. N row y and n column I. B is matrix 1 theta 3 theta 1. So first we run the matrix function, then we combine in matrix 1 theta minus 3 minus theta 3 minus theta 1 1. What are theta 1 to 3? Basically in theta we have what? Alpha 1 alpha 2. In theta we have how many? Alpha 1, not alpha 1, sorry. We have beta 1 alpha 1 beta 2 alpha 2. So theta 3 is beta 2, theta 1 is beta 1, exactly minus theta 3 minus theta 1 1. Why minus, you might ask? Because we are taking stuff on the left hand side, right? Whenever we are measuring beta, we're taking it on the left hand side, y1t minus beta 1 y2t. So we are left with minus estimator. The coefficient will be minus. Very simple. Theta 2 minus theta 4. Okay, fine. Then rows are simply positive. So row theta 5 theta 6. So row 1 2 row 2 1. So row 1 1 row 1 2 row 2 1 row 2 2. So theta 5 row 1 1 row 2 1 theta 6 row 1 2 row 2 2 theta 7 theta 8. Okay, so these are the thetas. Then we need to construct this. So we put all these in matrix function. When number of rows are 2 and rows grow, number of columns are 2 because the rows grow by t. Now we need to concentrate the residual now we need to construct the residual and concentrate out the covariance matrix. So to construct the residual, first we need to put the zeros, we need to create residual arrays. So u equals 0s tn v 0s tn, and in R how we do it, we run a function called array of zeros for t rows and n column, combining t rows and column, array for zeros combining t rows and n column. The question is why n column? Because we are dealing with multiple equations, and hence we are dealing with multiple multi-dimensional matrix. So now because we have two lags and two equations, we'll start from 2 because s t equals s plus 1, which is 1 plus 1. So start from 2. Y beta y plus ax, this is the reduced form. V is u minus ut minus rho ut minus 1. This is simply the reduced form. U is equal to beta y plus ax ut minus 1. So we are estimating that I is R is simple, omega is then we use V to draw our omega. Then we do log likelihood function, and the log likelihood function is simply this one, where half log twice by absolute value of determinant of B log of determinant of omega, and so log determinant of V log of determinant of B, and this is omega, right? Capital V is omega, and decomposition, that's all. And then we trim the first log likelihood functions. No, we trim the first row so that the dimension matches, because we are dealing with lags, obviously. AR1. So this is unconstrained log likelihood function. Any tricks in R that we need to concentrate out? No, we need to just simply for I in 2 to t. Fine. Then as you know, we don't need to mention how many rows we need, third bracket. because beta y, this is reduced form, these are already in matrix form, xa, so percentage sign, ui, beautiful number. We don't need to mention, talk about columns here, I minus 1 multiplied to row, fine, beautiful. Then we have omega, then array is zeros with combined t1. So negative constraint log likelihood function is rows are zeros, that's all. We set all the rows, the row correlation coefficient to be zeros, and that becomes your constraint log likelihood function. You create the matrix with this. We have done this before, so the same thing. Then we go to our main program. So we can either run simulate data or Gauss data. So here in R we didn't do the simulate data. I would generally do the simulate data. So I would create a simulate data function in R and then we'll do it. I'll just ask the system to use the simulated data. Then our Gauss data simply load from system. If we run the system, then Gauss data generally reproduces. This is another way to run simulation. If you ask the system to load system.mat, then Gauss data generally automatically reproduces this, and we want this to be as a matrix, y and x to be as matrix. So this is one way. These are the theta initial values given to us. Then we run the equation, we run the optimization, right? Then log L a1 minus t minus 1 1. You may ask the unconstrained log likelihood, how is it coming, where is it coming from? Just have a quick look. This is the unconstrained log likelihood. You see 1 by t minus 1 log likelihood, that's all. So minus t minus 1 multiplied to a1. This is how it is produced, and then inverse of Hessian is the variance covariance matrix, and then the constraint model. Again, constraint minus t minus 1 a naught. Fine. Then LR test is taking the constant and unconstrained difference. Degrees of freedom is important. We keep forgetting about degrees of freedom. It's good to test degrees of freedom every time. Degrees of freedom is length of theta 1 minus length of theta naught. So these two log likelihood, the theta 1 minus theta naught, who is okay, theta 1 is being estimated here, theta naught is given, so the difference is degrees of freedom. Theta 1 minus theta naught. All the thetas are saved here. So we are seeing if we have lost any of the in constraint we don't have the autocorrelation function. So theta 1 has an additional row parameter, theta naught doesn't have the row parameter, so obviously with no autocorrelation there is 1, so that is the degrees of freedom, and that we need when we are finding the p-value. LR test of independent autocorrelation, L12 L1 independent. How are we getting L10 L log L 0 log L1 log L1 log L2? Did we do log L2? Oh yes, this is the constraint log likelihood, this is the constraint log likelihood, constraint model. This is unconstrained log likelihood minus t1 into a1. a1 is the log likelihood function, we are multiplying with minus t1. a0 is the log likelihood function, value of that, multiplying with minus t minus 1. That's all, constraint log likelihood. So yeah, fine, this is very easy. Independent word test of no autocorrelation. So first we have the 4 parameters for well how many are we testing? That is the question. Let me check. Okay, see, we have 4 parameters from LR1, LR2, alphas, betas, all are 4. So here we have the equation is are we talking about 4 equations here? Yeah, I think beta 1, beta 2, alpha 1, alpha 2. No, this is first order vector autocorrelation. Systems of autocorrelation are we talking about here? So okay, just have a look. So because there is y2 and there is lags, that will be multiplied to having number of correlations. So 0 0 0 1 first, these are not the lags, these are parameters themselves, then come the lag and 1. Then it will follow the structure here 1 1 row 1 2 row 2 1 row 2 2, because we are well constraining the rows. We'll talk in detail about this kind of wall test in chapter 13. Right now, generally when we do it, you see we have to create one index, and then from the index we need to know where the rows are located, and we put 1 against them. So you have 4 parameters that you are estimating. No, 1 2 3 4 5 6. 1 2 3 4 5 6 7 8. You have 8 parameters. So you have 8 parameters that you are estimating, right? And what are these parameters? Where is our row located? That is the question. So our rows are located in, let's see, 1, 0.6, 0.4, 0.2, 0.5, 0.6, 0.4, 0.2, 0.5. Beta 1, alpha 1, mm-hmm. 0.6 alpha 1, 0.2, 0.5. I'm not sure where 0.2 is coming from. 0.2 minus 0.5. Okay, fine. 0.8, 0.1. Okay. This is how it's going. Basically, you have to write down the equation to understand this. Then the common autocorrelation. So we'll discuss this in detail in chapter 13 when we actually deal with system of autocorrelation. Okay. So we know how the functions are, and optimization is that wall test is a confusing part, and for that we need to go into detail for wall test. Lagrangian multiplier is simply, well, degrees of freedom, and then use numeric gradient, and this is we have already done this before. Okay, so there you go, the system is gone. basically wall test in system of equation is difficult because major the major errors occur when we fail to recognize which coefficient should be located in what cell or what array in the index. And so it is suggested that when we are doing the system of equation, remember everything will be replicated for one autoregressive parameter. So all the variables, all the parameters that are coming once, they will be coming again for the lag as well. And so we generally need to do a calculation, and then we need to set zeros according to the size of the index that we estimate. And then looking into the index, we need to probably with pen and paper we need to identify out where the coefficient that we are trying to test against are turning to 0. So that is a difficulty in wall test in system of equation, but that is widely used. And so when we move into the discussion with var models and S-var models, we'll see a lot of use of it. I'm not gonna spend time talking about that, because right now without looking into the theories, without explaining how wall test is done in system of equation, jumping into a problem will not be productive. So problem 8, illiquidity and hedge funds. The data consists of 1869 daily returns for the period of 1st April 2003 to 28 May 2010 on 7 hedge funds: convertible arbitrage, distressed securities, equity hedge, event driven, macro, merger, equity market neutral, and 3 market indexes: Dow, Nasdaq, and S&P 500. For each of these 7 hedge funds, we have 7 hedge funds here. Estimate the KPM. This is the equation in which R8 is the return on hedge fund, MT is the market return, F is the risk-free return. Interpret the parameter estimate test for an AR1 disturbance term. For each of these 7 hedge funds, you estimate a dynamic KPM where reapply LM test to estimate the residuals. Great. So first we need to see we have local functions. Yes, log likelihood function BYM. Okay, so B, this is Y, probably this is Y, yeah, and then M. Beta parameters, we're gonna find beta parameters, beta naught, beta 1, and rho 1, beta naught, beta 1, and the correlation coefficient rho 1, all into theta parameters. U equals y minus beta naught minus beta 1 into M, y minus beta naught minus beta 1 into M. Okay, y minus beta naught minus beta 1 into M. Maybe we're not talking about F right now in the risk interest rate. 1 into M. V is equal to 3 mar U1 0 minus rho 1 3 mar U0 1. Fine. Sigma square is V square. Log likelihood is t is greater than 2. When t is greater than 2, that is a log likelihood, the conditional log likelihood function. This is exactly the same thing. We have included the library beta naught, beta 1 rho, beta naught M, rho 3 mar, y0 1, mean V square, log twice pi. Beautiful. Return log likelihood function. Then let's go to the equation. So we load the data. Then excess return, we need to find the returns. So hedge fund excess return rate is 1 to 7 is the hedge funds, and 11 is risk-free rate, which is repeatedly created for in 7 columns, and then gives us the return. MRO, exactly in the same way we do calculate all the returns. Then we create dummy variables, right? Season, hedge data 15 to 18, Tuesday dummy, Wednesday dummy, Thursday, Friday, and holiday dummy. Okay, fine. dummy variables are created. How do we create dummy variables? D season H data 15 to 18, all rows 19. Oh, they're already there. So choose a H font, fine, length, LM test applied, keep them with AR1 disturbance term. So first OLS, column bind T1 and M. M is what? M is market return, right? Market return, yes. So we just in X we put the market return once, column bind once, then we do OLS of Y and X, right? Y is any H font, M is SP 500, fine. Then V is equal to Y minus XV, beta X. Z on the other hand is once, now lag, taking the lag, trimmer M10, trimmer V01. Z is trimmer M10 means MT minus 1 VT 10, and V is trimmer V10. See, trimmer V01 VT minus 1 VT and VT minus 1, that's all. So we allowed once to mess it up, T minus 1, then we start cutting off the first row, beginning with cutting off the first row, then trimmer V01 and trimmer V10, and then we do the regression again. E is equal to V minus Z beta 2, beautiful. Then we have R2, which is 1 minus E transpose regressed on V minus in V. Oh, okay, this is divided, not regression, sorry. Divided by this, U square divided by V minus mean V square. T minus 1 multiplied to R2 is LM. Okay, and then chi-square CDF LM1 P chi-square. With AR1 estimated KP model, without AR1, and with AR1 we have theta naught given to you. What are the theta naughts? Yeah, probably theta naught is what are the theta naught parameters? Have we estimated the theta naught parameters? Probably not, we are just assuming. Okay, fine. AR1 disturbance, so we do maximum likelihood estimation and parameters are estimated, fine, with an initial, we initialize with any random values combined. So this is the tweak, C combine, that's all. We want Hessian too, so Hessian comes up. So now we compute residuals U Y minus theta 1 theta 2 M. M is with beta 1, so Y minus theta 1. We trimmer U10 theta 3, trimmer U01, beautiful. Theta 3 is row. Then allow Z to mess things up. T minus 2 1, then trimmer first T0 T20, trimmer V01 V10. Okay, we're not messing much up. V01 V10 is not going forward because M1 has been calculated. This is M2. Okay, T minus 2 we have. Okay, again do the regression, LMT minus 1 R square. So that's how you do it. Compute the residuals twice. First compute LM applied with AR1, compute the residuals, then estimate the model with AR1, and then we compute the residuals with the MLE estimation with OLS with MLE, and then wall test 0 0 1. Obviously in the last parameter we have correlation coefficient, either it's 0 or it's 1. last one is residual. So simply do this. That's all. We have done this many times now. Okay. This is auto hedge. This is hedge fund calculation. At the end, what did we find? We estimated all the parameters for the 7 hedge funds. We actually basically estimate the KPM, capital asset pricing model, for the hedge funds with this little bit of code. What we did first, we introduced our log likelihood function, which was conditional one. Then we did OLS. OLS don't have AR1, so without AR1 we do OLS. Then we do MLE with AR1, autoregressive one, and in between, see, X, Y, and V. You have U, equation of U. Equation of U was not there. That's the only part. AR1 disturbance, but equation of U is used here. So this is the only part that is drawing the line, and everything else you did in the previous portion. So basically that's it. And then voltage is not necessary, but you can check if there is autocorrelation or not. So the question was, for each of the estimated dynamic KPM, where this is the residual series or autocorrelated residual. So we're doing estimated test to see if they're autocorrelated or not. That's all. Fine. Great. Then finally is the Beach Mackinnon study. Bias, we did this already. You see, in previous examples we dealt with, we already kind of use this. The flag one, remember, with flag we use FN insert. Exactly the same problem. Beach Mackinnon, there's nothing changing. We generated data, we estimate exact MLE, we estimate conditional MLE. In exact, flag is 0, in conditional, flag is 1, and then we do OLS, and then we do efficiency test, which one is more efficient compared to the others. Mean squared error, root mean squared error. So conditional exact, OLS exact, so we check the efficiency. So this is exactly the same problem as what we dealt with before, so I'm not gonna go on spending time on this. Thank you. This concludes well, autoregressive chapter 7 autoregressive models which are not system of equation. Next I'm hoping to cover system of equation. Thank you.